As per IS 1893 Part 1 2002, sorry, design spectrum method, the design horizontal seismic coefficient H of a structure shall be determined by the following expression. H is equal to Z by 2, I by R, and SA by G. Z is the zone factor, which is given in table number 2, and it depends upon the seismic zone. For different seismic zone, different values of Z is given in table number 2. I is the importance factor. You can see table number 6 of IS 1893 Part 1 2002. Depending upon the importance of the building, you have to take the importance factor. R is the response reduction factor. You can see table 7. Okay, for different type of building systems, you can get the values of R from this table. Okay, then SA by G, right? SA by G is the average response acceleration coefficient. Okay, this is the figure given in the code for 5% damping. Three graphs are shown over here. This is for type 1 soil, that is rock and hard soil. This is for type 2 soil, that is medium soil. This is for type 3, that is soft soil. Okay, right. 5% damping is recommended for concrete structures, and the corresponding factor is taken as 1. Okay, so for 5% damping, the corresponding factor is 1. Now code is given table number 3. Okay, for other factors, multiplying factors are given for other damping percentage, right? Multiplying factors for obtaining values of other damping. Okay, so you can use this table for taking the factors, multiplying factors for the other percentage of damping. Okay, now fundamental natural period. The approximate fundamental natural period of vibration in second of a moment resisting frame building without brick infill panels may be estimated by the empirical expression. Ta is equal to 0.075 h raised to 0.75 in RCC frame building, where h is the height. Okay, the approximate fundamental natural period of vibration in seconds of all other buildings, including moment resistant frame building with, this is with brick infill panels, may be estimated by the empirical expression. Ta is equal to 0.09 h divided by under root d for RCC frame building. D is the base dimension of the building along the direction of the lateral force. Okay, so if your lateral force is in this direction, then you have to take D equal to this, right? And if your lateral force is in this direction, then you have to take D equal to this, right? So this will be D in that case. So you have to take the dimension along the lateral force, right? That is what the code says. Base dimension of the building along the direction of the lateral force. Okay, now we will do a cross check of a design example uploaded on website by IIT Kharagpur E26, whose link is shown below. Okay, live load taken on floor is 1.5 kN per meter square, and live load taken on typical floor is 4 kN per meter square. So table number 8 is given in the code, which shows the percentage of imposed load to be considered in seismic weight calculation when the live load is up to including 3 kN per meter square. Then the percentage of imposed load to be taken in the calculation of seismic weight should be 25%, and if it is above 3 kN per meter square, then the percentage of imposed load to be considered in calculation of seismic weight should be 50%, right? As in our case, live load on typical floor is 4 kN per meter square greater than 3 kN per meter square as shown in table 8 above. Okay, we will have to go for 50% reduction in the live load. Okay, so this is our plan. Okay, we can see the plan is symmetrical about both the axes, right? And it is a square building, right? So this width is 22.5 meters and this length is also 22.5 meters. Okay, so there are 6 stories. I call this story as 0, 0, 1, 2, 3, 4, 5 and 6. Okay, So this is terrace level, this is fifth floor, this is fourth floor, this is second, this is third, this is second, this is first, and this is ground. So this is the seventh slab, this is the sixth slab, this is the fifth slab, this is fourth slab, this is third slab, this is second, and this is first, right? So that is how I have mentioned over here. So these are the seismic weight of the floor. This is the seismic weight of terrace level, this is the seismic weight of fifth floor, this is the seismic weight of fourth floor, and so on, and this is for the ground floor. These are the height from the base. So the ground level is at 1.1 meter from the base, 1.1. First floor is at 4.1 plus 1.1, that is 5.2 meters from the base, so 5.2. And terrace is at 30.2, right? So this is how this this detail has been tabulated, right? Now, this cream shaded portion, you can see, will pass on the load to the terrace level. This cream shaded portion will pass on the load to the fourth floor. This cream shaded portion will pass on the load to the second floor, and this cream shaded will area will pass on the load to the ground level, right? Similarly, this pink shaded area will pass on the load to the fifth floor. This pink shaded area will pass on the load to the third floor. This shaded pink shaded area will pass on the load to the first floor, right? This is how the load is distributed to the floors, right? Okay, so this thing is repeated over here. These are story levels: terrace, fifth floor, fourth floor, third floor, second floor, first floor, ground level. These are the corresponding seismic weight. This is the total weight, that is total seismic weight of the building. These are the seismic weight of the individual floors, right? So this is the total seismic weight of the whole building. Okay, these are the corresponding heights from with respect to the base. This is Wi by h square. Okay, and this is the total, that is sum of this, that is sum of Wi by hi square, right? Okay, now we want to find earthquake forces Qi, right? So this is the formula for finding Qi: Wi h square divided by sum of Wi by hi square into Vb. Vb is the base shear. So let us find the base shear first. Okay, the approximate fundamental natural period of vibration in second of a moment resisting frame building without, our building is without brick infill panels, so we will take this formula: Ta is equal to 0.075 h raised to 0.75 RCC building frame. So total height is 30.2. Okay, 30.2. So we'll take h is equal to 30.2. So this value is equal to 0.9661. Okay, so our footings, the footing of this building are resting on medium soil, so we have to find SA by G. So let us see the section for SA by G. Now the soil is medium. Okay, so we have to see this table. Okay, and our T is 0.9661, which falls within this range. So SA by G is equal to 1.36 divided by T. So we will use this formula for finding SA by G. So SA by G is 1.36 divided by TA, that is equal to 1.36 divided by 0.96619, which is equal to 1.4076. Okay, now we have to take the importance factor. This is an important public building, so the importance factor we will take from the table is 1.5. Okay, important service building, so we will take 1.5, and the zone in which this building, the seismic zone in which this building falls is zone 3, so Z is equal to 0.16. okay, so we will take Z is equal to 0.16. okay, so importance factor is 1.5, Z is equal to 0.16. Now response reduction factor, we are taking R is equal to 5 because our is a special RC moment resisting frame. Okay, so we can see from the table that for that the importance response reduction factor is 5. Okay, so now getting all the values, now we can find our AH, that is equal to 0.0337. okay, now VB is equal to the total seismic weight into AH. Total seismic weight we know it is 39286. okay, so 39286 into 0.0037, this is equal to 1324. This is our base shear. Okay, Actual value is 1323 point something, but I've rounded it off to 1324. Okay. Now you can very easily find QI. QI is WI h square divided by sum of WI by h square into VB. Okay. So for terrace level, WI by h square is this. Sum of WI by h square is this. Okay. So into VB, that will give you this value, that is 480.45. Similarly, for fifth floor, this divided by this into VB, this is VB, that is equal to 381.39. So this is how you get this value, that is lateral forces, earthquake forces at each level, right? Now after finding this, you find the shear story, right? Okay, story. So for this terrace level, the story shear will be 480.45. For fifth floor, the story shear will be this plus this, that is equal to 861.84. For fourth level, it will be this plus this plus this, that is equal to 1106.9 and so on. Okay, so this is how you get the story shear, right? Okay, now we can make our life easy by making a program which directly gives us the earthquake forces. Okay, we will see, we'll try to run that program. Okay, so we'll run this program. Okay, before going to into the program, I will show you some pages. Okay, this is a very important page which explains that how is the seismic weight calculated, and after the doing the calculation of seismic weight, how do we get the center of mass, right? Then this shows that how do we calculate the center of rigidity. Okay, so in this case I found the center of mass to be over here and center of rigidity to be over here. So this distance is known as static eccentricity, right, which we have to consider, which we'll see later, right? And this page shows that how do we calculate the rotational stiffness of the story, and this page shows that how the force, lateral force acting at the center of the mass, is distributed as nodal at the nodal points, right? Okay, now we will run the program first. Okay, so the total height of the building is 30.2 meters per center. Total number of stories is 0 plus 6, so I will give 6 over here per center. Okay, okay. Height of the typical story is 5 meters per center. Class number, okay, hour is 2. Okay, so write 2. And then earthquake zone is 3 per center. Importance factor, okay, importance factor, our is an important public building, so we will write 2. Okay, by writing 2 over here, the program will take importance factor as 1.5. Okay, so 2 press enter. Write the total width of the frame is 22.5 meters. Okay, fine. Press enter. And the type of the soil, is medium 2, right? So write 2. Okay, now press finish. Okay, okay, we will have to give the response reduction factor on the command prompt screen. Okay, please wait for the command prompt screen to populate. Okay, right? So yeah, to give a total story load from the screen, write 1. We are giving the input from the screen, so we will write 1. Okay, okay, write the load in kilonewton for the floor 1. So what I'm doing is, what I'm going to do is, I'm going to give this input data, load, seismic weight of ground level and its corresponding height, similarly seismic weight of first floor and its corresponding height, and so on, right? So that is what I'm going to do, right? So load is 2027, press enter. Height is 1.1 meter from the base. Okay, total load on floor 2 is 6138. Okay, and the height is 5.2. Press enter. Total load on floor 3 is 6381, and height is 10.2. Okay, okay. Then total load is on floor number 4 is 6381. Okay, and it is height is 15.2. Okay, again 6381, height is 20.2. Okay, uh, again the load is 6381, height is 25.2. Okay, and on the terrace level the load is 5597 and height is 30.2. Okay, okay, so if there are brick infill panels we would write 1, but we don't have any brick infill panels, so we'll write 2. Okay, value of response reduction factor is 5. Okay, so we can get the output, right? So this is how we get the output. The lateral load at 30.2 height from the base is 481, at 25.2 is 382, at 20.2 it is 245, and so on, right? So we can cross check with the manual results. Okay, we get over here 480.45 at terrace level, right? That is 30.2 is the height, right? And over here we get 481.6. Slight difference is coming because we have considered this as rounded figure, that is 1324, actually is 1323 point something, right? So that is why a slight difference is coming. Okay, so this is how you can use the computer program, which can make your life easy and save your time, right? Okay, now moving further, note that the building structure is identical along x and z direction, and hence the fundamental time period and the earthquake forces are same in both the direction, right? So what does this means? That this earthquake forces which we got are going to be the same in x direction and y direction, right? Because our frame is symmetrical. Okay, right, we'll see this in detail. Okay, now the code says that you have to take the design eccentricity, that is EDI. For floor I you have to take these two equations. Okay, these two formulas are given in the code. You have to take the most severe of these two, right? What is ESI? ESI is static eccentricity at floor I, defined as distance between center of mass and center of rigidity. That is what I explained over here. Let me go back and show you again. Okay, so this distance, this is center of mass and this is center of rigidity. The distance between these two is known as ESI, right? This is ESI, static eccentricity at floor I, defined as distance between center of mass and center of rigidity. Okay, so code is taken as 1.5 because we are increasing the actual eccentricity by 50%, right? But in our case, okay, as the building is symmetrical, okay, our center of mass and center of rigidity fall at the same point. Okay, so ESI is equal to 0. Okay, so that is why I have taken ESI is equal to 0. So the only thing remaining is 0.05 B1. What is B1? B1 is the plant dimension of the floor I perpendicular to the direction of the force. Okay, so if this is your lateral force, then B1 will BI will be this, right? Sorry, it is not B1, it is BI. Okay, okay, so BI will be this. If your lateral force is in this direction, then your BI will be this. But in our case, the width and length of the building are the same, 22.5 meters. So BI is equal to 22.5 meters. So the minimum eccentricity to be considered is 0.05 BI. That is equal to 0.05 into 22.5. That is equal to 1.125 meters. Okay, fine. So this is the center of rigidity and center of mass for this building. So which is that point, this point I have shown over here, right? This is C, center of mass and center of rigidity for 7th floor, terrace level. This is for 5th floor, this is for 4th floor, this is for 3rd floor, this is for 2nd floor, this is for 1st floor, and this is for ground level. Okay, now this is the force. Okay, lateral force or earthquake force in positive xx direction. Okay, for the terrace level. Okay, for the terrace level, we found that the lateral force is 480.45. So this is 480.45 in x direction. Similarly, this force is also acting in y direction, that is for 480.45, right? Okay. Similarly, this is for fifth floor, fourth floor, third floor, second floor, and so on, right? Okay. Now we have to consider a minimum eccentricity E for both the cases. Okay, so this force will produce a torsion moment which will be equal to this force into this eccentricity, that is 540.5. So let me explain you. This is in along xx direction, right? So this is forces along xx direction. This is 480.45 with a torsion of 540, right? Okay, so this is say the terrace level. Okay, now similarly, this will give, this force will again give an another torsion moment. Okay, when we are considering this alternate. Okay, so E is equal to 1.125, right? So M is equal to 540.5, right? So this is your say terrace level, okay, slab, and this is your lateral load, that is 480.45, and this is your torsional moment, that is 540, right? So this is how this which we this case which we saw was for the terrace level. Similarly, you will have for the fifth floor level. Okay, so this is a load with this moment, this is a lateral load with this moment. Okay, uh, so I hope I made my point clear. Okay, so this is how this thing is represented over here. Okay, now this, there are 25 load combinations used for design. Reference EQ26 example for 6-story building by IIT Kharagpur, right? So this is the table given in that example, okay, by uploaded by IIT Kharagpur. Okay, so DL means dead load, IL means imposed load, EXTP, EXTN, negative EXTP, negative EXTN. What does this mean? Okay, we'll try to understand that. Okay, fine. EXTP means earthquake load in positive X direction. This is positive X direction, earthquake load with torsion positive. So this is torsion positive, right? Now, EXTNN means earthquake load X positive in positive x direction, in positive x direction with torsion negative. So torsion is in this direction, right? Right, now what does this mean? Negative extp means earthquake load in negative x direction, so it is in this direction, right? With torsion positive, so torsion is positive. Negative extn means earthquake load in negative x direction, in this direction, with torsion negative in this direction. Okay, so this is how this is also applied to the y direction, right? So all these cases have to be considered for doing the analysis, and you have to take the most critical one. Okay, so this is how we find the earthquake loads. Okay, and these loads are acting at the center of mass, right? So we have to distribute to the nodal points. Okay, right, to get the nodal loads, right? So pyi, okay, is distributed as p1i to p4i in the ith story junction according to the sum of the column stiffness in line of the force, right? So this force, part of this force will go over here, which will depend upon the stiffness of this column line. Okay, part of this load will go over here, which will depend upon the stiffness of this column line. Similarly, this column line and this column line. In our case, all the columns are of the same size, simple, so this will be divided by 4. Okay, this will be py by 4, py by 4, py by 4, py by 4. Now we have an additional torsion moment. This will again give rise to additional load at each junction, right? So that has to be found as, by this formula, additional force due to torsional moment at node to be added to pi, that is torsional moment, this is torsional moment into distance between the column line in the column line considered, okay, in consideration, and center of the rigidity. So suppose we are considering this line, then we have to consider the distance between this column line and the rigidity, center of rigidity. Okay, so we have to consider this distance, that will be this. Okay, so torsion moment into this distance divided by the rotational stiffness of the story into the stiffness of the column line in consideration, stiffness of this column line, right? So this will give you the additional force which has to be added over here due to this torsion. Similarly, you have to find for this level, for this level, for this level, right? So this is how you get the final P1i, P2i, P3i, P4i in this case, and similarly you have to find for this case also, right? So this is how we do the distribution of our earthquake loads acting at the center of mass to the distribute as a node loads, right? Node load. These are all called as nodal loads, right? Okay. So that is how we do the calculation for the earthquake forces. And now a very important point is given in the code, that is torsional irregularity, right? Code says, say we are having a lateral force in this direction, right? So this point is displaced over here, then this displacement is delta 1, this point is displaced over here, and this displacement is delta 2. Okay, when delta 1 is greater than 1.2 times the average of delta 1 plus delta 2, okay, then you can say there is torsional irregularity. Okay, similarly you have to check in this direction also. This is delta 1, this is delta 2. If your delta 1 is greater than the average of delta 1 plus delta 2 into 1.2, then you can say torsional irregularity is present. Okay, okay, so please visit uh, website MMS program. I am writing over here, so you can try to remember. Visit website MMS program civil dot com for this video and its PDF, right? Right? Okay, so I hope you must have found this video useful. Thank you.